So limit laws tell us how we can apply limits when we have a bunch of functions combined together, such as, added functions, subtracting functions, dividing functions and multiplying functions and so forth. So suppose we have two functions Now this is the simplest case. Of course, you could have more than two functions. You could have 2, 3, 4. But concept is quite straightforward. So if we have a limit and we want to apply it to the sum or difference of two functions, all it is telling us is that we can apply the limit for each of them individually and add them together or subtract them from each other. Likewise, if we have the limit of two functions in multiplication, then we simply apply the limit for each of them first, and multiply the limit directly. And the last case is if we have limit f of x over g of x, then we could simply do the limit for the numerator and the limit for the denominator. There is also the power case where if you have, so I should not have mentioned last case, but the power case, if we have f of x raised k, then we can apply the limit for the function inside the power, then take that limit value and raise it to the power of k. The difference quotient. The difference quotient is simply the slope of a secant line of a function written in a different way. So suppose we have a function and I'm going to pick 2 points, x and x plus h. H is some real number. So since the value of x is x for this point, so we will simply have f of x there, and the value of x is x plus h over there, so that would be f of x plus h. And if we draw a line between these 2 points, that would be the secant line. And we know how to find the slope of the secant line. It's just the slope of any line. So the slope here would simply be equal to f of x plus h, y2, minus y1 divided by x2 minus x1. So f of x plus h minus f of x divided by x plus h minus x. The x's will get cancelled and we would simply have f of x plus h minus f of x divided by h. And that is what we call the difference quotient of a function f of x. The difference quotient is important because it kind of connects the theory of limits with the concept of derivatives, and we can find the derivative of a function or understand the theory behind the derivative of a function using the difference quotient, which we will see later on. So here we have a function which is going, we want to find the limits of this function, and it is a product of two functions, a product here and the product there. So what I'm going to do is apply the limits individually and simply multiply them. And based on the power rule that I wrote over here, if we have some function raised to the power, we can directly apply the limit to the value and then raise it to the power. What do I mean by that? Here the limit is x approaches -1, so I could directly say -1 raised 4 minus 3 times -1, so we have 1 plus 3, we get 4. And the next bit is would be x squared plus 5x plus 3. Here we have three individual functions. X squared is a function, 5x is a function, 3 is a function. Add them all together, you get another function. But what does the limit law state? The limit law states that we can apply the limit to each of the functions, and so we have -1 squared, 5 times -1 plus 3. So 1 minus 5 plus 3, we have 4 minus 5, we get -1. So we now have two individual limits for the two functions that were in the problem in product. So we simply have to multiply them. So 4 times -1, and we get -4. Extending the same idea, we have two functions that are in product. So we apply the limit x approaches 8 to each of them individually and multiply. And we have a power over here, which is the third root of x. And since x is inside the root, we can simply move the limit inside the root and apply the limit. So I have 1 plus the third root of 8, which is simply 2. So 1 plus 2 is 3. The second part of the function has three individual functions, which are 2, 6x squared, and x cubed. And the law states that if we have functions added or subtracted, we could apply the limit to each of them individually and combine them. So the first term has no x in it, so the limit doesn't affect that particular constant term because there is no x. It was the same in the previous part right here. There was no x in the first term, so the limit x approaches 8 did not affect 1. So we'll simply have 2 minus 6 times 8 squared plus 8 cubed, which would give us 2 minus 6 times 8 squared, 1 minus 8. So we'll have 2 minus 64 times 6 times -7. It's 2. We could use a calculator here naturally, but 360, 384, and 384 times 7. It's 28, 58, 5, 0.2690. Let's just verify this with the calculator. I don't want to confuse you. Oh. Well, seem to be way off here. I wonder how that happened. Should have just relied on the calculator. Oh. Let me try this again. Okay, so it happens to be 130. I was, in fact, way off. So here we simply multiplied 3 times 130. We get 390. So now we have a case where we want to apply the limit, and we have one function divided by another function, and we have a square root. So we can move the limit inside the root. And if we apply the limit, the numerator would become 2 times 2 squared plus 1. The denominator would be 3 times 2 minus 2. And we'll have 8 plus 1 divided by 4, which is square root of 9 over 4, which is 3 over 2. So here is an interesting case. If we apply the limit directly to this problem, we would have square root of 1 plus 0 minus square root of 1 minus 0 divided by 0. We'll have square root of 1 minus square root of 1 over 0, which is 0 over 0. When it comes to limits, 0 over 0 is not 0. This is what we call an indeterminate form. There is a rule called L'Hopital's rule, which we can use to find the limit, but we can't use it here because that rule depends on derivatives. So how do we go about doing this without having derivatives? We have to use a bit of algebra here. So what I'm going to do is I'm going to try to remove the root in the numerator with a technique called rationalizing. So if you recall in algebra, we can multiply it by the conjugate. So the conjugate here for square root of 1 plus t minus the square root of 1 minus t is simply the square root of 1 plus t plus the square root of 1 minus t divided by square root of 1 plus t plus square root of 1 minus t. If we FOIL the numerator, we would end up getting square root of 1 plus t squared minus the square root of 1 minus t squared, and the denominator would remain as is. So we will have 1 plus t minus of 1 minus t. The square and the root will get cancelled. That goes away, that goes away. And divided by square root of 1 plus t plus square root of 1 minus t. Distribute the negative. The 1s would get cancelled and we'd have 2t over square root of 1 plus t plus square root of 1 minus t. So we have one function divided by another function, so we could apply the limits individually. So 2 times 0 divided by square root of 1 plus 0 plus square root of 1 minus 0, which is 0, divided by square root of 1 plus square root of 1, which gives us 0 over 2. So in this problem, it ended up being 0, but we cannot simply say 0 over 0 to be 0. It is what we call an indeterminate form. So we've got to be careful when we deal with indeterminate forms. So here is another case where we have 1 over t times square root of 1 plus t minus 1 over t. Let's go ahead and apply the limit directly and see what happens. The law states that we can apply the limits to each of the functions. So 0, square root of 1 plus 0 minus 1 over 0, which would give us 1 over 0 minus 1 over 0, which if we rewrite it 1 minus 1 over 0, which would become 0 over 0. If you can't see it directly, we could also rewrite it as take the common denominator. So I multiply and divide by square root of 1 plus t. So I have a common denominator now. Now, if you apply the limit, it will still result in 0 over 0. And keep in mind, we can't just jump to a conclusion and say 0 over 0 is 0 when it comes to limits. So it is an indeterminate form. We'll talk about that later. So how do we find the limit? We use the same trick that we did previously. I'm going to multiply and divide by the conjugate to rationalize the numerator. So the conjugate of 1 minus square root of 1 plus t is 1 plus square root of 1 plus t. And if I FOIL the numerator, I'll get 1 squared minus square root of 1 plus t squared divided by t times square root of 1 plus t times 1 plus square root of 1 plus t. So limit t approaches 0, we have 1 minus 1 plus t, because the root and the square would get cancelled, so those two would just go away. And we divide that by t times square root of 1 plus t, multiplied by 1 plus square root of 1 plus t. So the numerator, as I mentioned, would simply reduce to negative t. So we'll just go ahead and change that. If we distribute, so that will become negative t. So if you look closely, there is a negative t or t there and a t there. So the function would reduce to limit t approaches 0, negative 1 over square root of 1 plus t times 1 plus square root of 1 plus t. If we apply the limit, we'll have negative 1 over square root of 1 plus 0, which is 1, times 1 plus square root of 1 plus 0, which is 2. So we end up getting negative 1/2. So what you saw at the very beginning, 0 over 0, is not the answer, because if you said 0 over 0 is 0, then that is the wrong answer. 0 over 0 is an indeterminate form. So here we have to do something algebraic to get the correct limit. So the golden rule of thumb here is anytime you have 0 over 0, it is an indeterminate form, so you have to do something algebraic. One of the common ways is to go ahead and use a trick like we did over here. So we want to apply the limit h approaches 0, x plus h cubed minus x cubed over h. If you apply the limit directly, you will get 0 over 0. So you would end up getting let's see, x cubed minus x cubed divided by h, and x cubed minus x cubed is 0. The limit for h is 0. So 0 over 0, it is an indeterminate form. So don't just put the answer as 0. So what can we do algebraically to avoid this problem of getting an indeterminate form? So I am going to FOIL the numerator and if I FOIL, that's what I would get. And I am going to get rid of the x cubed terms. That's going to go away. Oh, I'm sorry, this term is xh squared. hx squared. So we will end up having limit h approaches 0, 3h squared x plus 3hx squared plus h cubed divided by h. What do we have in common in the numerator? We have a h in common. So if I pull that out, I would have 3hx plus 3x squared plus h squared divided by h. So the h's would go away. Now I'm going to apply the limit h approaches 0 to each of those terms. The first term has a h, so the first term will go to 0, so that's going to become 0. The second term doesn't have a h in it, so it remains as is because it is a constant with respect to h, so 3x squared. The last term has h squared, and if you apply the limit, that would become to 0. So the answer is 3x squared. So at the onset, we had 0 over 0, and if you just call the answer to be 0 at this step, then you may, oops, didn't mean to do that. If you said the answer is 0 at that step, you made a mistake because that is an indeterminate form and that cannot be just 0. So the correct answer here is 3x squared.